Okay, well, hello everybody. Welcome to the next installment of our reading group. Today, we're really excited to welcome Luka, Ribar, and Ivan Chelombiev. They're both researchers working at GraphCore, and today they're going to be going through their paper on SparQ Attention, bandwidth-efficient LLM inference. For a very quick background, on Luka. So yeah, he's a research scientist at GraphCore, working within the research team on developing ML algorithms and applications, exploiting the unique architecture and performance capabilities of their IPUs. Previously, he was a research associate in the control group in the engineering department at the University of Cambridge. Likewise, Ivan is also a machine learning researcher at GraphCore as well, working on attention-based neural architectures and sparsity with a passion in problem solving in ML and in machine intelligence. Previously, he did his bachelor's and his master's in computer science at the University of Bristol. Again, really, really excited to welcome both of you today, to go through SparQ Attention. The floor is yours.
Hi, it's really nice to be here. We're getting some duplicated voice signal. I don't know if you have that on the stream as well.
I would suggest maybe not watching the stream is potentially an idea, actually. Might be best for everyone that's in here, maybe just to be on the Google Meet, because we typically don't watch the YouTube stream at the same time. But hopefully now I shut up. Maybe now I stop talking. Hopefully it won't be a problem. So I guess if you guys share the screen, maybe it fixes itself, hopefully.
Okay, cool. It sounds like it's not a huge problem.
Oops. So yeah, if you just press the kind of arrow in the box pointing up, hopefully you're able to do a screen share. I always have this. There we go. Amazing.
Yep. Let us just try to figure this out.
Yeah.
Sorry, son.
No worries. Always.
Do you guys?
We see the screen. Yeah.
Our presentation.
Yeah, we see. Yeah, see it now. Perfect. Might be worth, if you guys have the YouTube stream up as well. Sorry, I should have maybe said this before. I guess if you've got the YouTube stream, you're going to hear the volume coming from the actual Google meeting and the YouTube stream. Might be worth kind of maybe stopping the YouTube stream or something like that, maybe. But otherwise, it'll be mainly you guys talking, and you won't be able to hear your own voice on the video. So hopefully there won't be a volume issue. Hopefully.
Yeah, because we joined from a room, so I think we have a sort of a double stream going from the from the speakers and from the stream.
And so, well, I guess if I stop talking and just you guys are presenting, hopefully that's not a problem. I guess let's see if it works.
I think if I talk, we'll also hear ourselves as well. So
sorry, yeah. Let's.
Do we want to maybe let's just jump into the smaller room?
Yes, let's see. Yeah, I mean, you just make from this screen for the same effect, like if you're on a big screen. Yeah, just disconnect from the screen.
Apologies.
No worries at all. Unless maybe you kind of only shared not the YouTube link. I guess if you stop having the YouTube and you just share your actual screen of this meeting, that might be better.
You don't have YouTube on that. No, yeah.
The perils of live streaming. We have this all the time, every week.
All right. Do you see the presentation?
We actually see your notes right now. Actually, sorry. That we saw it then. Yeah. Yeah, we see it perfectly now. Yeah.
Okay. Cool.
Amazing. Yeah. So do you wanna? Yeah. I think it all looks good. Yeah. Feel free to start whenever you're ready.
Yeah. Can you hear us?
can hear you, yeah, although we can see we can hear you and we can see the first slide now, yeah.
Yeah, okay, cool. Yeah,
Amazing.
sorry for the technical issues. We don't usually use Google Meet, so yeah, that
No
took a
worries at
while
all.
to figure this out.
I know the feeling.
Yeah, so it's a pleasure to be here to present our work. Yeah, thank you so much for inviting us. And yeah, so we're Team GraphCore. GraphCore is a semiconductor company. We produce accelerated chips for machine learning. So we target most of the machine learning workloads, kind of similar to how people use GPUs, but we have designed a new accelerator, which is sort of built from ground up for machine learning and has a lot of very cool properties, and it allows us to work on on the machine learning algorithms sort of from the ground up and see how they could be executed much faster. And especially there are a lot of the interplay between the memory and the compute is kind of fully reconfigured in the IPU, which is the chip that we produce. And this motivates a lot of our work. And so I'll introduce kind of like the authors of this paper. So my name is Chelombiev. I've been working on NLP models at GraphCore for the last 4.5 years. And mostly using the transformer architecture and seeing how that could be improved and what kind of things we can do with that. And
yeah, so hi, I'm Luka. Yeah, I've been at GraphCore for around 2 years now, and I've been mostly also working on language models, and yeah, so the focus being sort of on efficient inference sort of as of late, so which is what we're going to be talking about today.
Yeah, and we also have one of our co-authors on this paper, Charlie Blake, just sitting there in the background. And yeah, this work has also been done with Luka and Carlo Luci and Douglas Orr, who are hopefully watching the stream online. Yeah, all of us work in GraphCore research. I think we have quite a few areas of interest. So we work with NLP quite a bit because it's such a big machine learning workload for a lot of people who use AI. And we also do a lot of work on AI for life science applications and numerical formats for machine learning applications as well. So you can follow more of that on Twitter, where we share our papers, and we also do like a monthly papers of the month review where we cover some of the papers which we enjoy. So let's talk today about the paper that we did, the SparQ Attention, which is a specific attention mechanism for inferencing large language models. And I guess to begin with, I'll just cover the sort of the basics. So this is the transformer architecture. It came out amazingly 7 years ago, and it has been a very popular thing for NLP, and people from various fields are using this architecture now, and it's very versatile and allows for powerful scaling. And the kind of the structure of the transformer model has changed only slightly over the last years, but it still kind of remains in a sort of the same, where we embed some sort of discrete signals through an embedding and turn them into hidden vectors. We put some positional encoding into these vectors, and then we apply a stack of transformer layers sequentially to sequences of these discrete tokens. And the transformer layer is made out of 2 parts. It has a feed-forward layer, which is just quite a simple, machine learning, general building block where we just pass through a couple of dense layers. And then there's the multi-head attention mechanism, which is kind of like the secret sauce that makes the transformer work. And if we focus on that specifically, the way how it works, in a classical formulation, that we have these 3 our features come in, and then we have these 3 tensors, query, key, and value, and we produce sort of attention scores based on queries and keys, and that allows to mix information very efficiently within the sequence between different tokens. And it turns out just doing this operation allows to do very powerful modeling on all kinds of discrete sequence tasks. But let's jump into more detail how this works exactly. So we have the query and key multiplication first. Then we scale this by the square root of the dimension of the model. We apply the softmax operation and multiply all of this with a value tensor. The additional complexity here is that it's a multi-head attention, so we do actually a multitude of these operations in parallel, but we can drop this complexity for the time being, as it's not very important. So the query and the key, the interesting features here is that they are of dimensionality of the sequence length and feature length. So for each token is a vector of some feature length, and then we have a certain number of these tokens. And then when we multiply these two tensors together, we get something that is of dimension sequence length times sequence length, which is kind of a very cool and interpretable thing because we can see how the tokens interact with one another. When we train bidirectional transformers like BERT, all tokens within a sequence sort of talk to each other and exchange information, and we see how one token affects the other token and how related they are. Because if you get a very high score, that means that the tokens have a lot in common and have a lot of information about one another. And if we get a very low score, that means that the tokens don't really need to interact that much. And with the latest models like GPT, which are causal in their nature, the tokens only look into the past, into the history. So what we're trying to do is to do the next token prediction task. So based on the sentence so far, how can we produce another token? And this is kind of the fundamental way how all of these models are trained today, as far as we know. Because a lot of research is being more opaque these days. So once we have these scores, we do the scaling. Why do we need to do the scaling? Because for each one of these sort of individual cells, we do a dot product of D items, which are normally, well, we assume kind of like normally have a normal unit distribution, and then doing that, that sum produces something that has a variance of dimension D. So if we multiply it by the scaling factor of square root of D, we kind of fix that. Charlie is the expert on scaling, so he can say a lot more on this. And this sort of comes into play in our SparQ Attention mechanism. Then we do the softmax to convert these sort of values which are all over the place into something that looks like a probability distribution, because all the values sort of start being in the range from 0 to 1. And they also sum to 1. So that means that we can interpret these scores very, very well and get these things that are like probability distributions. So that's much easier to work with. And then in the end, we apply these scores to our values, which means that the information within the sequence is kind of mixed with one another. So we each token gets the value of each token gets a chunk of the value from all the previous tokens sort of summed into it, and that sort of allows for a very efficient way of mixing information on the sequence axis rather than on the feature axis, which is then later done in the MLP layer.
And very quick question, sorry. Again, this might be a stupid question, but are we currently talking about the standard mathematical expression of transformers, or is this equation something in the top left that's a bit unique to your approach?
No, this is just the very standard transformer from the Vasvani transformer. So
exactly.
That's the paper from 2017. So this is just this has always been the case for multi-head attention.
Okay. Perfect. Yeah. I want to make sure I was following us. So just kind of we're setting the scene for kind of the nature of the computations that are required for transformers, basically.
Yeah, and another important point here that this is the computation during the training. So during the training, all these sequence tokens interact with one another. So that's why the query here is of the shape of sequence length and features. And we get these attention maps which are quadratic in sequence length. So they're basically square. And I think a lot of sort of efficient transformer attention work has been focused on trying to address this quadratic issue. But this is mostly a training thing, because what we are working with is an inference mode, which is somewhat different, where the kind of the queries that come in, they don't have a shape of sequence length. They just have a shape of one. So it's just a one single vector that is coming in. And then we're multiplying it with the keys from all the previous history to see how this one token interacts with everything else that came previously in the sequence. So this is just like the only small change that we have from going from trading to inference. But kind of an efficiency that we can see here, that on every single new token that we generate, we don't need to recalculate the whole history of the keys and values. We can just stash them away, and once we have a new token, we can just take this history and generate this attention map again, just appending just one extra vector to that history. And that results in what is called a KV cache, which is used during transformer inference. And it's quite a big tensor. So it's like in the bottom row, you can see the shape. It's like a 6-dimensional tensor, and it grows together with the batch size and the sequence length, which is something that is also some axes which are dynamic during inference. So for example, the number of layers in a transformer wouldn't grow, but you can choose your batch to be whatever. So this is kind of like a very alive thing, and it occupies some space. And just for context, if we want to see, like if you're using a Llama 7 billion model, which is quite popular for like a very small LLM, well, small today, I think, like a couple of years ago, it was a huge thing. If we have 1,000 tokens in a context, then computationally, what this would look like memory-wise, the weights of the model occupy 13 gigabytes of memory, and then the KV cache, which you would need, is only 500 megabytes. So it's really not much of an overhead, and your main headache with this model is transferring the weights, which is the main consumer of memory. But if you say you want to have a context window of 1 million, which is not that crazy anymore, because Gemini 1.5, which was released, I believe, a couple of months ago, has a 1.5 million context window, which is enormous. And you want to put more stuff into the context, because you can then use in-context learning. So say you have a 1 million token context, which is a very useful thing. But what would your computations look like? Well, you still have the same weights, because weights are independent of the batch or the sequence length. So that doesn't change. But suddenly the KV cache becomes 500 gigabytes. So weights are no longer your headache. It's this enormous cache. And just to put this in context, 500 gigabytes is it's a very significant thing. So if you ever think of transferring data over the wire, say from your laptop to a USB, a 10 gigabyte film takes a little bit, but if you want to transfer half a terabyte, that's almost like an overnight thing. And what's even more problematic here is that, when you do like a lot of computation and then you need to do a lot of memory transfer, it's not too bad, because you're doing a lot of work, but also you're doing a lot of transferring. And that's kind of what it works when in the pre-fill stage. So when you have a very long prompt and you're or an embedding, if you pass it through the model, it's all done in parallel with one another. So there is a lot of work for the accelerator to do and a lot of transfer to do of the memory. But once you go into the to the next steps, where we generate one token at a time, this issue of having 500 gigabytes of cache is really, really bad, because you generate one token. That's not even a word. It's like half a word. And for every half a word, you need to transfer this half a terabyte object back and forth just to produce that one half a word. And going back to the analogy, it's like it's an overnight job with a sort of normal computer to transfer this much memory. So this is really, really challenging. And this is the issue that we're trying to address with SparQ. And I think Luka is going to give even more in-depth analysis of this issue.
Yeah, so basically what I was explaining was that, once we're in this kind of token by token generation mode, we're in a mode that's not quite ideal for the hardware that we generally use, right? So one way you can think about this is if you consider what's called arithmetic intensity, which is essentially how much work, like how many floating point operations you do per data transmit, right? So like the way I think like the most useful way, at least for me, the way to think about it is that I quite like this cartoon from I think this quite famous blog, right? How to make GPUs go burr from back in the day. But I really like this analogy, which is you can essentially think about your hardware accelerator as a factory, right? It's producing stuff. And then next to the factory, you have sort of your storage space, which is the memory. And you basically need to fetch stuff from the from the storage space to the factory and process it, right? And how efficient you're being at this is determined by essentially two numbers here, which is how fast you're processing stuff that are in the factory and how fast you're bringing stuff to the factory. So your memory bandwidth and essentially flops per second. So when you think about sort of like what sort of workload is good for what sort of hardware, this is sort of a useful measure to think about. And so if you think about a workload, you might think about, okay, so how much memory, how much stuff I need to transfer and how much work I'm going to do once I transfer that amount of memory, right? And that's going to determine if your workload is sort of well suited for your fabric or not, right? Now, you can do that for some like hardware. So for example, like here are some numbers where essentially we kind of compare the operations per sort of memory transfer. So if you look at sort of, for example, H100, right, which is sort of now the kind of de facto standard, it's like, in 200s, whatever is this arithmetic test, how much work we can do per what we transfer. Now, the problem is that this is great for training, where we're sort of doing a lot of work, we transfer a sequence and we do a lot of work on it, right? But for token by token, the problem is that we don't really do a lot of work when we generate that one token, but we're transferring quite a lot of information as Ivan was showing. So the point being here is that our hardware, the way it is not very well suited for inference of transformers, right? It's great for training them. But for inference, we're just wasting a bit of the compute that we have. And the way you can think about it is that, so here we're essentially plotting this arithmetic intensity of a transformer layer. So it's like a generic transformer layer. And the way we sort of plot it here is that on the x-axis you have your batch size, right? So how much things you're doing in parallel, and on y-axis you have the arithmetic intensity, right? And we want this arithmetic intensity to be reasonably high, right? So 100, 200, 300, right? We want it, that's sort of the numbers that would be well adjusted for our hardware. Now, what you can see here is like we parameterize this because it's sort of a useful way to parameterize this equation is that you can consider this rho, which is essentially a ratio of your sequence length to the model size, right? So it's kind of determining how big our sequence that it's currently processing is compared to how big our model is. So if the sequence length is small, like rho is small, right? That's the blue lines here. It's not that bad. So you can fix your sort of how bad this is by batching stuff, right? So we transferred the whole model. If you're only doing one token, it's bad. We transferred a lot. We didn't do a lot of work. But if we transfer a lot of tokens, a lot of sequences at the same time, it's fine. We can, make our hardware, be busy because it's processing a lot of stuff. However, as the sequence length grows, this becomes problematic because your KV cache is growing, and that brings your arithmetic intensity all the way down. So you can see as you kind of go from blue to orange bits, you're pushed all the way one, and batching is not helping you anymore. And that's the problem. So if you want to push sequence length, we need to do something about it. One thing you might think, like, well, maybe we should do grouped query, and maybe we probably should. It's a great idea. It does make things better, but it's limited again to an extent that it can make it better. So if you look at sort of the graph on the right, like it looks better than the graph on the left because as you push sort of, to the orange lines, you kind of get limited by your group size. So the bigger your group size, the better it is for your arithmetic intensity, but you're still not quite where you would like to be. So that's kind of the setup. Like this is what we would like to address. Okay, so how are we addressing it? So, well, the first thing to note is that the attention scores are sparse. So what do I mean by that? So when you have essentially your token that you're currently generating, and you calculate attention scores across the whole history, and you look at those scores, they're not like evenly spread, right? Actually, your current token is only going to attend to some parts of the sequence. And you can visualize that in many different ways. One way you can visualize this is, for example, here on the right. So, take your favorite model, say Llama. So basically plot your attention for like all of the heads in the model. So essentially here you have x-axis is layer and y-axis is different heads, right? So there's how many heads? 32, I guess. And each point in this matrix is basically, so say you have a sequence like on 2000, right? Take the top 32 scores of that attention score. So that all of those scores would sum to 1, as I was showing, right? So take the top 32 scores and sum them. How close you are to 1, right? That's essentially going to tell you how much you're capturing just by taking these top scores. And what you can see here is that apart from the first couple of layers, actually taking these top scores keeps a lot of the whole weight. And what's basically this is telling you is that tokens tend to concentrate on only a few tokens at a time, and it's not very flat, this distribution. So how can we use this? Well, one way of using this, and this is sort of an idea that's in this flagship paper, where essentially the authors have a lot of clever ways of fitting things into a single GPU. So one thing you can do is like, well, you calculate the attention scores. And now we know that a bunch of them are very near 0 or exactly 0, right? Well, we don't have to fetch those values anymore from the memory because the scores are going to be multiplied by something that's very small. So the idea here is basically calculate your attention scores and only bring the values that are going to correspond to the high scoring, right? So to the high scores. And that obviously, like, if I'm getting only 32 values out of 2000, that's quite an advantage. So that works great. The problem with that is that here we still had to download all our keys, right? We still had to calculate the attention scores, which meant we had to get all of our keys, and that still grows with sequence length, right? So we still have a problem. Like we can basically get rid of fetching the values, but we don't get rid of fetching the keys. So basically, can we do better than that? And the idea here is, well, can we predict which tokens for the current query, which tokens are going to be high scoring without having to bring all the keys from the memory, right? So that's kind of that's the goal. So I just wanted to first touch upon some other methods you might do for that, right? So how do you predict this kind of pattern, right? So one thing you might want to do is consider like a static sparsity pattern. So that means have some kind of a heuristic saying, well, tokens generally attend to like a few local tokens and maybe some tokens in the past, and fix that. So every time you have a new token, you apply exactly the same sparsity pattern, right?
Sorry, can I ask a very quick question, actually?
Yes.
Just very quickly on the last slide. So where it says top 32, what's the total size that's out of?
Yeah, that's a good question. So I think I
it's
believe
2000,
it's 2000 in this experiment, yeah.
2000?
Yeah.
Mm-hmm.
Okay, wow. So really kind of like almost the top 1% or so, roughly. Like 1% of the heads are kind of doing the vast majority of the attending, basically.
Yes. And
Yes, and it gets worse in the further layers. So the first couple of layers, it's almost some of the heads are doing near 0, so they're looking at everything, and then
But does that mean then? Does that mean that? Oh, sorry. But so the early heads. So the early heads. It says the sum of the top 32 attention scores. So basically, on these first two on the leftmost, are they then more distributed?
Yes.
Across the entire thing, right?
Yeah, exactly.
Yeah.
So they're quite flat. And now one thing also to note here, it's very model specific. So we were playing around with different models. And for example, this particular thing where you have these first 2 layers being kind of outliers is a very Llama specific thing. We did not notice this.
Interesting. So with other models, you actually see the sharpness of the distribution in the early layers as well.
Yeah, exactly.
And it means in this case, you couldn't apply the FlexGen trick to the first 2 layers of Llama, but you could apply it to every other layer, basically.
That is right. So or you could, but yeah, it's gonna. I think you still could. Like we for example, most of the time we were not changing per layer house, but you might want to do that, right? Because this would sort of indicate the first 2 layers. Maybe we should get more stuff, and then we're good to go.
And it's always a trade-off. Like 32 is quite a sharp value, but
sure.
sequence length is
Yeah.
2000, you might just fetch 1,000, right? If you do it like 50%, or yes, you said this is a 1% sparsity. So when you sparsify things to things, you usually tend to break it.
Well, there's still obviously even here though. I guess there's some because the highest at the bottom, like they're still quite red, so there's still quite an accumulation, I guess. Like
it is also head specific, but I guess across the heads you do notice that most of them are quite sparse. But people have looked into like heads, specific heads, and you can see very interesting stuff there as well. Some heads are more local, some heads are more global. But we're not kind of concentrating on it too much. We're just noticing that they're generally quite sparse.
Okay, makes sense. Awesome. Yeah, thanks a lot.
Cool. So just to kind of touch upon like different ways you might want to consider like attacking that. So one thing I said was you might want to consider a static sparsity pattern. So you're essentially saying every time I'm generating a token, I'm going to assume the same sort of pattern that's going to appear in the attention, right? And you probably have seen papers like that. They've been quite successful in different ways of doing this. But essentially what they do is they say, they usually have a heuristic of sort that's saying, I'm going to tend to the local tokens always. So, the closest 30 tokens always. Some tokens maybe in the past, either randomly or some other way, and maybe some initial tokens as well. So that's, for example, Big Bird on the left, like that was a pretty famous example of that. On the right, you have a more recent paper from LM Infinite, where the authors basically noticed that if you have a local window, just like a fixed local window, it doesn't work that great. But suddenly you introduced a few initial tokens of the sequence, and because of whatever peculiarity of transformer training, that often improved your sort of perplexity quite a bit. However, as you might think, like if you're completely ignoring everything in the middle between the beginning and the end, like surely sometimes you're going to miss out on some useful information. Now, another thing you might do is like, well, can you do something sort of more dynamic, more sort of, in line with what's going on? So you might consider, well, okay, I have this huge cache. Maybe some of those tokens are completely irrelevant, right? I can get rid of them. They're not important. Like then the question becomes, how do I find unimportant tokens, right? So that's the sort of, that's the difficulty here. So there were quite a few clever ways of doing that recently. Which we're sort of kind of calling here eviction-based methods. The one we mostly consider is this H2O. We have this nice way of thinking about it, which is basically, well, as I'm generating, I'm attending to everything in the sequence. I can keep track of how much I attended to each token, right? So, maybe just sum up the attention scores from the past. And then at each point, I can have some sort of way where like, okay, let's check what did I attend to, right? And everything that I didn't attend to, top like bottom something percent, I get rid of, like I just evict. So basically, I keep track of stuff that hasn't been attended to and just get rid of it in the cache, which is nice because it saves memory and it saves on transferring because you don't really have it in the memory anymore. Now, again, the thing here is that what we were sort of like, it works very nicely in some settings, but you can definitely envision settings where during your generation, you might have been concentrating on one part of the sequence, but then at some other point, you might start concentrating on another. So I don't know, maybe it's like a plastic example. I'm talking to ChatGPT and I plug in like all of the Lord of the Rings in the context, right? And I keep asking Lord of the Rings questions about the first book, right? It's not going to attend at all to the second or third book, right? Like, and then after a while, if I start asking about second book, like it might have gotten rid of some important stuff there because it just didn't care for it. So I mean, it's a very plastic example, but that's sort of the way of thinking that we had when we were sort of approaching this. Okay, so what is our approach then? So we had sort of a few kind of guidelines, like how we came up with our algorithm. So we started with saying, well, let's actually keep the full KV cache. So we're not going to do eviction. Like we might do eviction, like it depends also how aggressive you are, I guess. But for the moment, we're saying, no, let's keep everything. We consider we might need it at some point, but let's focus on trying not to transfer everything at every step. So the general setup is like I have an incoming query. I want to somehow decide based on the current query which parts of the KV cache are important so I can fetch them from the memory without like deleting it. Right? So that's sort of another thing. We could sort of do techniques that would operate in that space. And finally, what we were so far, at least, that we were concentrating on is something like I'm calling this plug and play here. But the idea was how far can we go without doing any pre-training or fine-tuning on the model? So we didn't want to do pre-training. Fine-tuning usually helps, right, when you're sort of messing with the model a bit. But I want to see, can we do this sparse kind of approximation without actually changing the model? So the model was trained as normally dense, right, like attending to everything. Can we now, at inference time, just attend to bits of it in a smart way that's not going to actually degrade the model? So that's kind of the
it's funny how much, so this sounds really super interesting. It's funny how much this starts to sound like retrieval augmented generation in the kind of KV cache and in the prompt space itself. Yeah. It's almost like you have a small context window and you do RAG, and now we have a long context window, but we still kind of need something that looks a bit like RAG in order to make it computationally tractable. It's really
yes, exactly. I think that's one of our big questions that we have is sort of like comparing, like, can we just use the our context as a kind of retrieval base.
Exactly, yeah.
And how does that compare to doing an actual retrieval? And actually, like sort of one of our bigger questions. Like one reason why people like to dump everything in the context is because it's easy, right? So,
exactly, yeah.
So there's, but maybe there's other reasons why you might want to do it. That's something that I think is like a long-term.
Yeah, and I guess a lot of these proprietary models that also do have their very long context length, I assume that they are doing, probably something that looks a bit like kind of RAG behind the context length anyway, kind of inbuilt into the prompt, and then enabling in the prompt is almost like a convenience of the user experience to some extent. Yeah. Anyway, very interesting. That's right. Yeah.
Oh, that's a great point because we were thinking about it exactly like that.
Yeah.
Cool. Okay, so to go to the approach, so kind of the basic assumption here, well, observation more, is that queries are sparse too. So what do I mean by that? So like when you have a query vector, we were analyzing sort of like how the query vectors would look like, and we noticed they're essentially dominated by few large values. So if you look at your query vector, it has 164 or whatever head dimension is 128. You look at sort of individual components, and you look and you sort of you plot it as a distribution. So on the right, we sort of we're comparing the distribution that we get out of these queries compared to what it would look like if they were normally distributed, right? On a log scale. It's just on the y-axis. That's why the Gaussian looks weird. But one thing that we noticed was basically that the tails are quite high, right? So compared to a normal Gaussian distribution, you're having quite a lot of sort of values that are kind of high magnitude values high magnitude values tend to have quite a bit of probability distribution, right? So that means they appear quite often, and they tend to sort of dominate then your vector products. So based on that, the idea was basically this. So we have the query. Can we only select for that incoming query the largest components? So, say top 8 dimensions out of 64, and then only base all our kind of calculations on only those 8 dimensions, right? So that's the idea. And then now I'm going to essentially run for the algorithm to kind of, because I think we have all the kind of building blocks to actually get it going. So this is the setup, right? So you have an incoming query. The matrix on the right is the keys, right? The keys matrix that's living in the memory, right? So the left is query that's currently in the hardware. So what do? So we first determine what are the top, we have a parameter R, and we select top R components of query, right? So R is like a hyperparameter that we tune. So once we have those top R components, then we only fetch the corresponding components of keys from memory, right? So in this case, we found these two components, number 1 and number 3, and we're only going to fetch those rows from the key matrix from memory, right? So now, when we have that, we're going to use that to approximate our attention scores, right? Because we don't want to get all the keys and calculate actual attention scores. We're going to use the dot product using only these dimensions as a proxy to find approximate attention scores. Now, we don't care too much if these attention scores are not correct, but what we are hoping for at this stage is that the ordering sort of is going to be at least correct, so that we're going to be effectively predicting what are the keys that will actually be high scoring if we got the full vectors, right? There's if you're following the algorithm on the right, there's some additional stuff on the temperature. I'll touch upon it a bit at the end, but for now, don't worry too much about it. Like you can just think about it as kind of getting an approximate ordering. Now, once we have that, we can proceed to do exactly that thing that we're describing for FlexGen, right? So get top K keys and values, but now corresponding to this approximate attention scores, right? And hope for the best. So in this case, we have another hyperparameter, which is K, and then we get top K keys and value pairs, key and value pairs for memory based on these approximate attention scores, right? Once you have those, you can then proceed to basically just do standard attention, like just using those keys and values. Or what we did was that we had an additional step. Now, why we had this, just to kind of give an idea what we're doing here is basically we're selecting, say, 32 keys and values from the cache out of 2000, right? That was kind of the example. So that means we're ignoring completely 1900 keys and values, right, from memory. So we thought instead of doing that, what we could improve a little bit is keep track of the mean value of the keys, of the values, and then kind of have a correction term that's going to add, a mean of all those 1900 other values. We don't know the attention scores of the kind of individual ones, but we thought, if we kind of add that as sort of a bias, that might actually be helpful. The difficult part here is like, how do you estimate how much you should associate to mean? And for that, we basically go back to our first step and we had approximate attention scores. So we can use that. We can look at our top K score, approximate attention scores versus all the rest. And that can tell us sort of kind of the how much relative weight we should give to our top K versus the average of everything else. But essentially that step is there to kind of help us like improve the approximation a little bit. But even without it, you could do the algorithm, and yeah, in most situations it worked pretty well. Okay, so now I'm going to be talking about how we evaluated the setup. Right? Okay, so just quickly on what we were using. So model-wise, we were basically using open source models up to around the biggest one was 13 billion Llama. So Llama Pythia, because Pythia was quite nice, you could see how things scale. And then Mistral, which is a very performative model, like sometimes better than Llama. But interestingly, also it uses group query attention, which was important for us, because our whole method depended on basically selecting parts of keys and values based on the current query. But in grouped query attention, multiple queries want to access the same keys and values. So if they all want to access different parts, you might end up in a situation where you're not saving anymore much. So we wanted really to test for that, and that's why we were very keen to have a model that uses grouped query here. So that's model-wise. Now, task-wise, so ideal task for what we were trying to play around with here is something where you plug in a bunch of text, right? And then you want model to basically, based on that information from the text, generate something, right? So the most natural task for that is question answering, right? So you give a text with some information, you ask the model to answer a question. And we sort of adapted kind of standard task for that regard, such as squad and trivia QA. But note that squad we made a bit harder because we added up a bunch of kind of confusion context. So we would essentially have a text with useful information and a lot of other text with not useful information to see if it can retrieve the right thing. Text summarization. So you give a text, generate a summary. Kind of general language modeling. So, just measure perplexity of the next word, which is a standard NLP task. And one thing that we sort of built for like kind of ourselves for this, which is which we're calling here text repetition, which is a simple task where you basically give a model a text, and then you prompt the model with some part of the text summary within there, right? And you ask the model essentially to kind of keep copy paste like from the text sort of continue, right? So imagine like in this case we have Shakespeare text. It's like Romeo and Juliet, and you tell model Romeo, whatever Romeo said, and you say Juliet, and then you want model to essentially copy from the text exactly, what was said, which can be quite a difficult task for these parse methods because you're essentially going to be accessing everything, right, and from your context. So we thought it would be a good sort of test bed for the sparse techniques. Okay, so result-wise, I just want to sort of explain the framework that we had. Was essentially we consider a single attention layer because we're concentrating on lowering the memory transfer for attention. And for all different methods, what we want to do is like we start from a kind of basic model that base model that work that densely attends to the whole sequence. We apply different sparsity techniques, and then we sort of push sparsity, right? So you can half, 1/4, and so on. So you push how little you're actually transferring, and you see how the accuracy falls off, right? So hopefully it falls off gracefully, right? And that's what you would like. So that's kind of the setup. Now, what are we comparing against? Well, okay, dense, as I said, it's just the base model. H2O is the eviction method that I was describing, where you evict tokens permanently after they haven't been attended to. FlexGen, which is the one where you get all the keys, but then not fetch all the values based on the scores. And LM infinite, which is sort of representing, I guess, like a few similar ideas that we saw in the literature in the last couple of years, which is this static pattern where you're basically having a local window, and you're also always attending to first few tokens, because that seems to be actually a big improvement compared to just attending to the local tokens. Okay, so those are the techniques, and so this is kind of our headline result. But all of the kind of tasks and models we plotted on this sort of plot. So the x-axis, you have how much memory you had to transfer, right, for that one attention layer. And on the y-axis, you have your actual performance, right? So the best you can do is your dense model. Right? That's what you started with. Like these things don't improve your model. They just hopefully don't degrade it while making it more efficient, right? So one thing you can notice, for example, for FlexGen, you have this kind of weird thing where it falls off at 1/2, but that's exactly what you would expect because you're always going to have to download all your keys, right? So you're expecting this asymptote when you're kind of, going very low there and you're just basically only having a few values. For the other methods, well, LM infinite, for LM infinite, this is quite a hard task because quad has information all over the context. So it's very hard to just get it from the local window. Well, eviction is doing pretty well, but what we notice is that already here, when you have sort of a bit more complex tasks like this, that eviction essentially would fall off a bit in accuracy as you kind of increase the compression. So we did this kind of plots for different models and different tasks. So essentially each column is a model and each row is a task. And we were essentially able to obtain similar looking curves. And I think generally what we saw was that our method fared quite well and was able to kind of pretty gracefully sort of go with the increased compression. One thing you might notice is that kind of the bottom one seems the hardest, and that's a repetition task, right? Because it's quite a hard task because you sort of have to kind of get actual tokens from memory all the time. And that's where, even for our method, that seemed more challenging, but we were able sort of to kind of keep up. While it's a very hard method for methods such as eviction, where you kind of get rid of things permanently, right? But yeah.
Sorry, very quick question. Sorry. So on the x-axis, when you're kind of doing a half, quarter, and eighth of the transfer memory, what does that correspond to in terms of the values of R and L roughly? I know you said in a way 32 up 2000, so it's almost like 1%. Are we talking? What kind of rough values are we talking about?
Yeah, that's a very good question.
I think you can kind of play with it. We sort of found a general recipe with our setup where we had sequence lengths of about 2000, where the R we could sweep from sort of 16 to so R would go basically from 12% to 25%, and the K value, which is another one, which is how much of the V tender you get. We used 1 to 8, which is again sort of 1/20.
I would need to think. I guess I'm trying to imagine kind of because I guess it depends on both the value of R and the value of L. I think it was these two hyperparameters that kind of specify. So I guess you tune both of these, and I guess because they have this kind of quadratic relationship in a way, it's got us. I don't know exactly what the relationship will be like with the memory transfers, but it was something in the order of kind of 12% in both of those, something like this. It wasn't as low as 32 though, I guess, because if you have 2,000, I'm assuming that, you know, I mean, 12% is looking more like 300 or something, not 32. So it was a little bit bigger than 32 example, I guess.
Yeah, so I think that's a good point. So because you remember, like we had 2 steps, right? In the first step, we sort of downloaded stuff based on the biggest magnitude of queries.
Yeah.
Like that's the one that actually dominates here.
Okay.
Because it's the one that scales with sequence length, right?
And that's
so
the value. That's the value R.
That's the value R. So that's the one that's kind of most important. Then K is obviously important, but what we found was that, you know, you can kind of flip it and it's not too much. Too important, but the R one is the crucial one. So,
but R was then on these experiments was typically kind of in the low hundreds.
Well,
was low.
So the one head dimension is 1 to 8. So we would use
yeah, okay, got it.
The R would be 16, or
yeah, got it.
Some models you can go as low as 8. It really depends on the task and the model. So I think it's something that you can play around with. But generally, we found sort of this 1/8 mark is where we can easily get to on most tasks and most models, and things didn't degrade. And so article 16 that worked great.
Yeah. I mean, we were trying to sort of like, you know, we did sort of like I was playing around with different parameters. So we were in this plot basically doing, you know, for a particular compression, what's the best that we were doing, right? Because you might have multiple combinations. But the other thing we tried here was to kind of be consistent with the parameters. So not to fine tune this to each model, but we have consistent R's and K's in these plots, even though for some models you might actually, but you know, we didn't want to go there because we wanted to see how general we can go.
Yeah, makes sense. Thanks a lot.
No, thanks. So I think we're pretty much at the end. So I just want to say, so kind of like the tasks that we're showing here, we're all up to 2,000 sequence length, right? So nothing too crazy yet, but one of the kind of longer term goals for us is really to understand how these things are going to scale with sequence length. So we did some initial sort of experiments on that, which is the plot on the left, where we tried to kind of go a bit further in the sequence length, here up to 12,000, using this Vicuna fine-tuned Llama model. And we found that, we're still able to keep up. But basically, what we would really like to explore is like, is this a technique that we can use when we go to 128K, or, you know, like we really think it is, but it's something that we would like to kind of do further experiments on. So for now, we're sort of relatively limited with
and
that.
We are waiting for an open source model to drop with a slightly longer context window, because not everybody supports these kind of crazy context links yet.
Most of them are. I mean, Pythia is only 2K, Llama is 4K, so it's relatively like we also wanted to stick with the signals like where the models are actually behaving well. On the other hand, so benchmarking is also another thing, obviously, that we would like to kind of explore further. We did some tests on the attention layer to see if essentially, we've shown that, you know, we can save on memory transfers, but like, can we basically move that to an actual practical speed up? So here you can essentially see some experiments on comparing kind of standard PyTorch attention to our implementation. And essentially, we were able to, so as you can see, sort of the red line, that's kind of the best we could do so far. And we were able to obtain the speedups, but we didn't quite hit sort of the theoretical limits that were sort of based on our work. And that's also one of the things that we're exploring now, essentially kind of further kind of fusing, kernel fusing in the op, right? How can we get this a bit closer to essentially what the theoretical speedup would be, and actually test it in a practical setup? So, like, a lot of the work so far was kind of focused on our building a framework, and I think now we're kind of hoping to move to that further stage. But
I think we're running quite short on time, so we do want to take as many questions as
of course. Well, first of all, thank you so much. That was incredible. So first of all, can we give a big round of applause, everyone, to both Luka and Ivan? We can do. I know a lot of people are going to raise their hands now because they get confused, but it's the emoji button and the hand clap. Yeah, a lot of hand raised. Might be questions, might be applause. We never know at the beginning. So, I certainly have questions, but first of all, all, maybe what I'll do is open it up to anyone else in the room. Otherwise, I'm very happy to kick off. But any questions from anybody in the room at all? I'll also quickly check the YouTube as well. Otherwise, I can kick off. I mean, I have a turn. I won't ask all of them. I guess the first question actually I just had on the last slide was, is that OpenAI Triton you're referring to, not NVIDIA Triton? I guess it's OpenAI Triton kernel fusion.
Yeah, like I mean, just
Yeah, I think so. Yeah.
Yeah. Okay. Yeah, it makes sense. I guess the first general question is how general is this algorithm then? Like, it seems like the concepts are kind of to some extent vendor agnostic. Is this the kind of thing that could actually show benefits to various hardware vendors, or are elements of it kind of very particular to the benefits that you see with IPUs? Kind of, yeah, how general is it?
Yeah, I think it's absolutely general. I guess it's the main thing. It's sort of going back to my slide. Is how big is your cache? You know, if your main headache is transferring the weights of the model, then it's not going to be super useful. But if you do work on long sequence lengths, or if you have big batch sizes where there's a lot of this cache, then suddenly this is the method that you want to use to sort of slim it down.
Yeah, I think one thing to note, like it's this kind of arithmetic intensity kind of that's optimal is actually very common for all the hardware. Like essentially, when we get to transformer generation, all of our hardware is much faster at computing than they're sitting idle, right? They don't have that work. So I think that's actually common to pretty much all the hardware we're using at the moment. So it's something that I think would need to consider for, because as we increase the bandwidth, we're also increasing flow, and you're still getting this kind of,
that makes sense. Another question I have is it was interesting when you mentioned about the bias term. So the fact that you can obviously take the most important, have a parameter R, take the most important 12% or whatever, but then you can kind of create an effective systematic offset that aggregates the other 90% or so. But you also mentioned that it was helpful, but not like super important. Like, did you do any ablations on how much that helped?
Yeah, we did. So one particular case where we found that very helpful was Llama.
Right.
And we actually suspect that it's because of those first two layers of Llama that we saw, right? So I think, like you could probably get around that issue in a different way, but with Llama we found that once we had it, we're suspecting that because it's fixing what you just saw in those first two layers, where it's very flat, so it's very helpful to have this like kind of average. But for some other models, we didn't find it helpful, so it's something that is still kind of.
It never degraded performance, though, I would assume, or did it sometimes?
There was one particular case, actually. So there was one particular case, which is why we were like keen to kind of explore it further and see because for most of the models it did not, right? Actually, for most of them improved, but then particularly for Mistral, I think what we observed was that we had a bit of degradation. So yeah.
Okay, that makes sense.
For Gemma, right? We didn't have that. No.
Yeah, for Gemma it was enabled. So we tested this on Gemma like last week, and Gemma works perfectly. It's just like no degradation with SparQ whatsoever. And it was with this mean value as well.
Yeah. I can imagine that the context length is gonna. I always do thumbs up all the time. I swear everyone in the world is like doing inadvertent thumbs up every meeting. What was I gonna say? I can only imagine in the open source space that there's going to be increasing context length, and that algorithms like this are going to become increasingly important. So yeah, really, really exciting. I guess it won't be too long until there's an open source model with a massive context length where this is going to kind of really shine. Fingers crossed. Yeah, I'll keep my fingers crossed for you. Another general question, slightly like broader, is kind of like, what are your thoughts on? I've not had the time to dive in, but obviously there was you showed some interesting results against kind of A100, H100. I know obviously Grace Hopper's been around for a while. Blackwell was announced like 4 days ago or something. Kind of, broad question. What are your thoughts on some of the latest technology that NVIDIA is rolling out? They're a little bit moving away from the general GPU and kind of, maybe this is a slightly broader question than just the research paper, but kind of what do you think about that in the light of IPUs and everything?
Yeah, I think the technology itself is quite strange. So having this much memory and such a low arithmetic intensity
Yeah.
I think we're in this weird space where the computers that we've been building for forever for accelerated workloads, they just don't really fit this type of workload. So I don't know who's going to fix it first. Is it the hardware that's going to jump to where the algorithms are, or is people going to drag the algorithms back to what the current hardware is? So I think it's a very difficult mode of execution. So I hope that SparQ sort of is one of the steps that people can take to reduce this headache, but it's a very awkward computational problem.
Yeah, I think even like with the new hardware also coming up, it seems to me like we're gonna still have this discrepancy between like the training is doing great, and then we go to inference and it's just things that are quite awkward.
And ironically, I think inference is where things are becoming increasingly important. Obviously, training is where you need tons of devices in parallel and you're doing very compute heavy stuff. But I think in terms of the world of Gen AI, like inference is an area where I think there's a lot of optimization still to be done, for sure. Super interesting. Well, last one. I guess I'm hogging all the questions. If there are any questions in the room, feel free to cut. I know we're at time, and I'm sure you've got places to be as well. Final one. Any other questions in the room? Yeah, Daniel Bar.
Yeah, hi. Can you hear me, please?
Yes.
Okay, so my question is also general. It's about the chips, the accelerators. I've seen language processing units. I tested it, the Grok accelerator. Yeah, it's very, very fast. And yours is also about for inference, right? IPUs.
Yeah.
Yes. So is yours faster? Is there a benchmark for all these? And is yours faster? And how can you beat them? Do you know how you can beat them or something? Because yours is very, very fast.
Very, very provocative question.
I think the main thing here is how many. I think fast is good, but like how much does it cost as well, right?
Yeah.
So if you have a Ferrari, which is 10 times more expensive than your average car, it's fast, but do you want to get a Ferrari just to be 10% faster? I think this is quite a big thing. I'm not sure. Somebody said that they used like 500 chips for the SRAM. Because Grok chips are built on SRAM, which is like 200 megabytes of SRAM. So I imagine just fitting one of these models is quite a struggle. I think everybody's struggling. And with NVIDIA, so the Blackwell, it has a 190 gigabytes of memory. But again, if you push this cache, if you have 1 million tokens and, suddenly, and even at, 4 bits, it's still going to be, a tight squeeze. And if your batch size is like 10, then I think we'll have to work with some sort of other memory systems which are not HBM because or SRAM. I think the algorithm increasingly pushing us towards sort of DDR memory, which is if you have a CPU that can work with that.
No. Makes sense. Thank you very much. Very comprehensive answer. It actually answered my next question, which was just kind of what are the next frontiers for optimization, and I think that kind of covered that one quite well. I think it's an interesting dance that's always happening between the algorithms pushing things forward, the ASICs trying to catch up. There's obviously a lot of startups now doing like heavily purely transformer-based chip design, and all it takes is a few algorithmic tweaks that are then, theoretically better, and that can kind of put them dead in the water. So the kind of the balance between generality and like being very good at Gen AI is a really hard one to get right, I guess. I guess what's going to be very good is being very good at MapMul and everything, but as you say, kind of getting the right balance of memory transfer and arithmetic intensity. Yeah. Anyway, I would love to kind of keep asking you questions and talk all day, but I guess we've all got things to get back to. But again, I just want to say again, it was great to have you. Again, let's give another round of applause for both Luka and Ivan. That was an amazing talk. And yeah, obviously there's going to be, I'm sure, many more great research papers coming out of GraphCore. So we'll love to have you again when you land the next one. And again, given that you're both based in London, I wasn't aware. We'll have to grab coffee sometime.
No, thank you so much. No, it was a pleasure. And please, if you have any further questions, reach out. Find us on emails or whatever. And
we'll do. Amazing. Yeah. Well, again, thank you so much for joining. And again, I hope everyone has a great week. We'll have another. I can't remember what we've got next week. We have another paper as always. So I'll see everybody again next week. And yeah, have a good day, everybody. Thanks a lot.
Thank you.
Bye.